Okay, another concept we need to talk about is power. Power, if you look at this, there are just a lot of different definitions that go into power. So we're going to try to tie some of these together. So back in last semester, we had change in energy over time as our definition of power. I believe we had that in the first semester. We have another formula that has the voltage, change in voltage, potential difference, is change in energy over Q, Q standing for charge. And we have that I is the change in Q, the change in charge, over time. And then we have Ohm's law, V equals IR. The main formula for power is P equals IV. That is kind of our main formula for power, and that is given to you on the AP sheet. We have to understand P is power, I is current, V is potential difference, which we also sometimes call voltage. But that's why it's V, is because of the voltage. So power is how much current you have and how much voltage you have multiplied together. But we can string those together because each of these different formulas is also going to be helpful. So this first one comes from this Q over T being current. Multiply that times V. We don't use that one. Well, we will use that one from time to time, but probably not as prevalent as some of these others. P equals IV is obviously, like I said, that's the one that's on the AP sheet. That's kind of the most common one. But we also know that V equals I times R, so if we plug that in, we'd get I squared times R. That is current squared times resistance. So we can find power by taking current squared times resistance. And we can do another substitution and find out that power is also equal to the voltage squared times the resistance. So a lot of different options here. Some of these are found on the AP sheet, others are not. Let's just take a minute to look and see which ones are and which ones are not. The most basic one is P equals IV. That is the one that's on the AP sheet. Over here on the side, I also have listed a couple others that are on the AP sheet. So these two are on there as well. This one, however, I squared times R, that's where we had to do some substitution. So that one is not on there. And I believe that would be the same thing for the last one. That was doing some substitution, and that's not on there either. So as long as you understand how they're related, you can get there. We'll just have to have some practice and when we're going to use which version. And another thing is that power are still in watts. And again, we talked about that last semester. Watts are a joule per second, and that is how we measure power. Same definition for power with DC circuits. Okay, let's look at an example. The glowing element in an incandescent light bulb, called a filament, is a long, thin piece of tungsten wire that is heated by electric current going through it. When connected to a 120-volt outlet, how much current does a 60-watt bulb carry? Okay, we are going to use this version of P equals IV, I equals P over V, because we're asking about current. Current is I. So we're going to have current, which is I, is equal to P, which is power, over V. Power is measured in watts. Okay, so when I'm looking for what power I should use, that's measured in watts. So I have 60 watts of power over 120 volts for my potential difference. And so now if I divide that, then I get 0.5. And this is current. Current is how much is going through there. That is amps. Okay. So again, just an example in how to use our formulas basically. Okay, similar situation for what about if it's a 100-watt bulb? Well, you're going to do the same thing, but this time we have 100 watts of power and 120 volts of potential difference. And if I divide those out, I get 0.83 amps. So the higher the wattage power, the more current you're going to have. Okay, for this next problem, what are the respective resistances of the 60 watt and 100 watt bulbs? So again, we had these situations. We knew the power, we knew the voltage, we found the current, but now what about the resistance? So in the margin over here, I kind of went through it. I hope you can follow it. We have the P equals IV. That's a formula that we know. That's a formula that's given on the AP sheet. We know V equals IR, once again, given to us. So I can plug in the IR in for the V, and so I get P equals I squared times R. So I'm going to start off with that equation in answering this question. Now, because I'm asking for resistance, I could also move it around a little bit and just divide by I squared so that I have it set up in the order that I want it set up in. So we're finding the resistance, and it's the power, so that would be a 60 watt, and that looks like a typo. That's just supposed to be 60 watt, not 600. That'd be a really bright light bulb. So we have a 60 watt bulb. The I is the current. That's what we just found, and we found it to be 0.5 amps. And that quantity is supposed to be squared. So we go to our calculator, we plug this into our calculator, take a second there and see what you get. Okay, when you divide that out, you should get 240 ohms. That is the resistance of the 60 watt bulb. Let's do the same thing for the 100 watt. You know how to set it up, so why don't you pause it here, get it set up, and see what you come up with. Okay, in this case, a 100 watt bulb, we take that 100 watts, divide by 0.83 squared, you have to square the 0.83, and we get 144 ohms of resistance in the 100 watt bulb. So less resistance here in the larger bulb, the brighter bulb. Okay, last question. The resistivity of tungsten, that's what makes up the wire in the light bulb, is given to us as this. If both wires have filaments of this diameter, how long is each wire? Okay, resistivity. Do you remember if that's an R or a rho? It's actually a rho, which kind of looks like a lowercase p, but it's like all connected and more curvy, kind of like that. Anyway, that's our rho. This is our, once again, I have that same typo there. Get rid of that 600 and make it a 60. That is our power. This is our diameter, which means that our radius is 0.020 millimeters. And of course, we want that in meters, so we have to move it over 3 more decimal places. Okay, over in the margin I have a couple of formulas. The first one is the formula that was given to you in the front page of these notes. It's also given to you in the formula sheet on the AP formula sheet. Once again, that rho, it shouldn't have that little pointy on there. I tried to find the best rho that I could, and that's the best I could come up with, but it does not have that pointy line. It's just a little hoop. If I rearrange that, because I'm solving for length, so if I rearrange this for length, I'm going to multiply by A, divide by rho, and I get my length. So I'm going to use this formula now to solve for my length. Okay, the length is the resistance times the area. Okay, we have resistance already. It's 240 ohms. The area is pi r squared. So we're going to take pi times 0.0002 meters squared, and we divide that by the rho, which is given to us as 5 times 10 to the negative 7th. And so before I plug this into my calculator, I might just want to check one of these meters is going to cancel with that meter, this ohm is going to cancel with this ohm, and we're going to be left in meters, which is length, so we're good to go. So take a second, put that into your calculator, see what you get. Okay, so you should have gotten 0.603 meters. That is basically telling you how long the filament is if the filament is 0.04 millimeters in diameter. So that is about a half a meter, a little bit over half a meter, which seems really long if you think about a light bulb. However, the filament is not just what you see. The filament goes in there and does wind around. like where you screw it in, it widens around in there. So that is a representation of how long that filament would be. We're going to do the same calculation for the 100 watt. So again, take a second with your calculator, plug this in, and see what you come up with. Okay, in the 100 watt bulb, you have 144 ohms of power. Okay, in the 100 watt bulb, you have 144 ohms of resistance. The area is pi r squared. And I think on the last one, I had the correct number of zeros up here when I calculated the radius, but I forgot a zero down here. But you should come up with 0.603. I just forgot to write in that extra zero. So over here, make sure you have 1, 2, 3, 4 zeros, and then you square it. And so that's for finding the area. And then our resistivity, that would be something you look up in a table or in a book or online or somewhere, and you get that information, and then you go ahead and divide that out. You should get 0.362 meters. Okay, let's think about what's going on here. Why is the wire in the 100 watt smaller than the wire in the 60 watt? Well, the resistance in the 100 watt is smaller than the resistance in the 60 watt. So to create more resistance, they made the wire longer. They could have made it skinnier, but it's already pretty darn skinny, right? So you don't want it so frail that it's going to break that easily. So in that case, this 100 watt is going to have a much smaller length, creating less resistance. Okay, we have quite a bit actually to write in the summary, but we can write that in there when we get to class tomorrow.